Hi, I am Tianze. This is my presentation of classic methods on TCP congestion control. First, let's see how congestion happens. The internet operates using a service model that is connectionless and best effort packet delivery. In accordance with the IP, this model is operated by switches and routers. The connectionless implies that each IP packet contains sufficient data and enables the network to route it to its intended destination without the need for a pre-set up process for packet handling. The term best effort indicates that the network does not provide any guarantees if a packet is lost, damaged, or sent to the wrong place during the transit. The network does not attempt to fix it. Handling such issues is the job of higher level protocols. This design leads to a situation where a source can easily send data into the network at a certain speed, but the data packets might run into a busy link somewhere inside the network. This link, being used by many different sources of traffic, acts like a bottleneck, slowing down the flow of packets. Given that the buffer space in the routers are limited, some packets will have to be dropped, which leads to retransmission, and these retransmissions actually intensify the congestion. So the core problem becomes how to balance the good put rate and the low frequency of discarding packets. There are a lot of methods in different domains. Let's see the design space. When managing resources in a network, we have to decide where to control it. Inside the network, like the routers or switches, or at the network edges, like computers or part of the transport protocol. It is not just one or the other. Both parts play a role, and it is about who does most of the work. Routers always choose which data packets to send through and which to drop. They can also decide how much they involve the end devices in this process. One way is for routers to let devices reserve space for their data and make sure it gets sent properly. Routers could use special rules and checks to manage this, only accepting data if there is enough room and making sure devices stick to their limits. On the other end, there is a method focused on devices at the edges of the network. Here, the routers does not promising anything or give any clues about how much data they can handle. They just stop accepting data when they are full. It's up to the devices to watch how the network is doing and change what they are doing based on that. In between these two, routers can help devices a bit more, not by saving space for their data, but by letting them know when they are too full. This approach, called active queue management, will be discovered later. What we have talked in class is window-based, and alternatively, you can figure out the speed at which the network can successfully send packets and adjust the timing of sending data to match this rate. This rate is simply calculated based on how many bytes are delivered over a certain period, like time it takes for round-trip transmission. It is important to understand this relationship between rates and windows, because a rate-based method is better for multimedia applications. These applications produce data at a certain average rate and require a minimum level of throughput to work effectively. Additionally, the main task of the end host is to figure out the network's available capacity, use feedback and observations, and then change how fast it sends data based on that. There are two main methods to do this. One is the aggressive method. This involves deliberately sending data at a high rate, leading to some data getting lost, and then adjusting the sending speed in response to this loss. This method is known as control-based, and another is a conservative method. This approach aims to spot early signs of too much data accumulating the network and slow down the data sending before it becomes too much to handle. We call this the avoidance-based strategy. When assessing how well a congestion control method works, we usually look at three key measures: throughput, delay, and fairness. Higher throughput is better, meaning more data transmitted successfully, less delay is preferable, ensuring data moves quickly, and the higher fairness is ideal, indicating an equitable distribution of network resources. Understanding throughput and delay is straightforward, but the fairness can be a little bit more sophisticated. Fairness is about ensuring each data flow gets a similar amount of network capacity. A simple way to think about fairness is trying to make the throughput for each flow as equal as possible. To quantify this, we use a formula known as the fairness index developed by Jane. This formula helps calculate how evenly the network's capacity is distributed among different data flows. So let's talk about control-based algorithms. This kind of method was originally put forward by Jacobson and Keras in 1988. There are several refined variants, and the widely used one today is called TCP cubic. The idea is accept ACKs and timeout signal to determine the congestion level in the network, and transmitter make necessary actions. There are some samples. This is the Jacobson-Keras algorithm. It is a new way to determine timeout and retransmit. The idea is the original method does not take the variance of sample RTT into consideration. If the variance of sample RTT is small enough, which indicates that the sample RTT is trustworthy, the 2 times of estimated RTT is too large for timeout. So this is the algorithm to calculate the new timeout. And then we could use the state transformation, which has been discussed in the lectures to determine the increase and the decrease of the congestion window. Then let's talk about the avoidance-based algorithm. Started at 1994, several avoidance-based congestion control algorithms were put forward. The idea is control-based algorithms accept signals which indicates congestion, then take actions to control them, while avoidance-based algorithm tries to detect where congestion will happen. If it detects some signal indicating the congestion will happen soon, it will slow down the sending rate to avoid the potential congestion. There are some sample algorithms. So this is the TCP Vegas. It first defined a base RTT and CWND. Base RTT is the RTT with no congestion commonly. It is the RTT of the first packet, and the CWND is the TCP congestion window size. The expected rate equals to CWND divided base RTT. TCP Vegas then calculates the current sending rate per round trip time, and then compare the actual rate and the expected rate. Calculate the difference between of these two, and the difference is non-negative. With the preset threshold alpha and beta, we can determine whether increase or decrease the congestion window. So let's talk about active queue management. The idea is that queuing overflow in routers is the core reason resulting to packet loss, and it is not only the consequences of congestion, but also intensify congestion. Since it happens in the routers, router is an ideal place where we could play some tricks to control the congestion. The routers monitor their queue length. If they think congestion is about to happen, they explicitly inform the end hosts. There are 2 main mechanisms, DEC bit and RED, random early detection. So the DEC bit, each router monitors the load it is experiencing. If the load is high enough, which means the average queue length is larger than 1, the routers will add a binary bit called DEC bit on each packet flowing through it to inform the receiver that the connection is in congestion. Then the receiver adds the DEC bit in the header of ACK to inform the transmitter that the connection are in congestion. Then the transmitter will adjust the sending rate to avoid the congestions. So this is how to calculate the average queue length. The threshold is determined by the average queue length. It takes the current busy interval and the previous complete cycle into consideration. Calculate the mean of the queue length in this average interval, and the formula, well, the queue length t is the queue length at time t. Yeah. And this is a RED, random early detection. Similar idea with DEC bit, but different in method to inform the TX and RX. It does not set the bit. It drops packets in a probability by which inform the end host implicitly, and different in method calculate the signal of average queue length. The decision depends on the average length, which is calculated by this formula. And sample length is the length of queue when a sample measurement is made. This queue length is calculated once when a new packet arrives at the gateway. And this is how it works. The job is determined by probability, which depends on the real-time average length when a new packet arrives. Set a maximum probability, minimum threshold, and maximum threshold. And with the and you can see how to determine the probability by this picture. So this is ECN. There are two special bits setting IPTOS field as ECN bits. One is set by the source indicating that ECN capable. This bit is called ECT. Another is set by routers indicating that congestion is encountered. This is a CE bit. You can see the pictures. Okay, and there are two more bits in ECN. One is ECE. Is ECN echo, which is sent by the receiver. Another is CWR, means that the congestion window reduced, and this is sent by the transmitter to inform the receiver that the congestion window is being reduced, like the just like the last transmission in the picture. So the performance, the first column is for job tail. The middle column is for RED without ECN, and the last column is for RED with ECN. The first two rows is about throughput, and the last three rows are about delay. So the result shows that the RED plus ECN improve the throughput with reduced delay, which is really cool. And let's talk about the pros and cons of ECN. ECN allows network devices like routers and switches to notify the sender of congestion before packet loss occurs. In traditional TCP, congestion is typically detected after packet loss has occurred, which is a more reactive approach. ECN provides a more proactive method by signaling congestion early. Reduced packet loss. Since the ECN enables early detection of congestion, it can help in reducing packet loss. In a simple TCP scenario, packet loss is the primary indicator of congestion, leading to retransmission and increased network load. Since ECN helps in avoiding packet loss, there are fewer retransmission required. This reduces the overall network load and latency, as retransmitting packets increases network traffic and delays. Better bandwidth utilization. With ECN, the TCP sender can adjust its transmission rate before packet loss forces it to do so, leading to more consistent and optimal use of available bandwidth. In contrast, the simple TCP often experiences a boom and boost pattern in bandwidth usage due to its reliance on packet loss for congestion feedback and improved performance in high-capacity networks. In modern high bandwidth networks, the likelihood of experiencing bursty traffic and sudden congestion is higher. ECN is particularly effective in such environment, as it helps in managing congestion before it becomes critical. And let's talk about the disadvantages. So for non-compliant ECN connections, a non-compliant TCP connection might falsely signal that it is ECN capable by setting the ECN field in its packets. However, it might then ignore any ECN notifications it receives. This misrepresentation leads to an effective congestion control, as the connection does not react appropriately to congestion signals. Also, a non-compliant connection could also ignore source quench messages, which are designed to tell a sender to reduce its transmission rate. Ignoring this message can lead to network congestion. There are also potential loss of ECN messages in the network. An inherent risk with ECN is that the message indicating congestion, such as source quench messages or TCP ACK packets with ECN file set, could be lost in the network. This loss means the sender does not receive the congestion notification, potentially leading to continued high retransmission rate despite network congestion. Also, there are differences from packet jobs. Unlike the packet jobs, which are a direct and unavoidable indication of congestion. The loss of an ECM message does not guarantee that the source will be informed of each congestion event. So this is all my presentation. Thank you for watching.